Okay, so in the second part of this lecture on what elements to choose, I would like to come back to more interesting problems that have saddle point structures. So let's say the mixed Laplace equation or the Stokes equation, or if you want to go beyond the Navier-Stokes equations, for example. So these are all problems where you have multiple solution variables that have different characters. So in the previous lecture, for example, I showed you the electric and the magnetic field, and this was also a vector value problem because you have 3 electric field components in 3D and 3 magnetic field components. But they all have the same character, whereas in the Stokes equation, for example, you have 3 velocity fields, or let's say 3 components of the velocity field plus a pressure. So velocity and pressure are completely separate and have different physical interpretations. And the equations have a much more block structure. So we had one lecture on the mixed Laplace before, and you saw how we decomposed this problem into blocks that correspond to, let's say, the pressure and the velocity components, and then how you manufacture this all into a solver, for example. So I would like to talk about how you would choose the finite elements in these cases. And so this is lecture 33 1/4 about how to choose the element for saddle point problems. So I would like to start with the Stokes equation. So in the Stokes equation, you would have minus Laplace u plus grad p, or if you wanted to, you can multiply this by viscosity, and you can also, like we discussed in the lecture on boundary conditions, replace this by divergence of epsilon of u. But that's not important for this particular lecture here. So let's assume I have this equation. Then I have minus Laplace u plus grad p equals f, and the divergence of u equals 0. And I can rewrite this in terms of a minimization problem. Namely, I would like to minimize the energy that is in this velocity field, and I can write this as 1/2 of gradient u squared minus the potential energy, that would be F times u. So where exactly this step from here to here comes from is not terribly important, but you will believe me that I can do this, that I can rewrite this equation in this form. Now, this minimization problem has a constraint, namely that I'm going to minimize over h1 functions that have d components, but all of the solutions that I care about must have divergence u equals 0. So they must be divergence free, right? That means that no mass gets lost. I cannot have a place where all of the flow goes in or all of the flow comes out, right? That's not physical. If I have a volume of air, if I take a piece of, let's say, a certain volume here, what goes in must come out. That's what this divergence constraint means. So I'm going to minimize this energy here on this subspace of functions that have divergence u equals 0. And if I do this, then I can also rewrite this second constraint here in a variational form, namely, so you think of this in terms of, let's say, a pointwise constraint. I like to think of this as a variational constraint, namely that q times diff u equals 0 for all q in L2. Okay. So the discrete formulation that we solve would be take this strong form here, multiply it by a test function, integrate by parts, replace all functions by a discrete subspace, or seek them in a discrete subspace, and that corresponds to the following discrete minimization problem. Namely, I want to minimize over the UHs in VH of this energy, and the constraints are now of the form diff UH times QH equals 0 for all QH. Well, that's a finite number of constraints now, right? It doesn't have to hold pointwise anymore, but it is as many linearly independent constraints as I have pressure degrees of freedom. So how many do I have? I have dim QH constraints on this velocity. And one of the things that is important to think about this, if you think about a minimization problem. So let's say, you have seen these problems in your undergraduate education. I want to minimize something over, let's say, a quadratic objective function subject to linear constraints. So I have a linear constraint here, I have a linear constraint here. Now, you can easily imagine intuitively if I have too many constraints, there will not be a solution anymore, right? I mean, let's say if I have a constraint that goes along this line, and a constraint that goes along this line, and a constraint that goes along this line, then there are no solutions, because there is no point where all three of these constraints meet. That's not exactly what happens in this case. So I don't have too many constraints on a finite dimensional space that prevent me from finding any kind of solution at all. But what I need to look at is if I go with h to 0, so if I make these spaces larger and larger, asymptotically, do I have too many constraints? And if I have too many constraints, that is exactly the case if the space QH of pressures is too large. Okay? Then I will have too many constraints, and in essence, the velocity, the discrete velocity that comes out of this minimization problem here, does just not have enough degrees of freedom to approximate the exact solution well. And what happens in a case like this is that the solution may not converge. So if I have too many constraints, the solution does not converge. I can reformulate this in terms of a mathematical inequality. So I can, this necessity to not have too many constraints is expressed by a condition that we typically call either the inf-sup condition or the Babushka-Bretzi condition or the LBB condition. And this condition looks like this. It says that the problem is only uniquely solvable with our discrete finite element spaces if there exists a constant c that is independent of the mesh size, so that the term that I have here in this bilinear form, that is the thing that comes out of either grad p or diff-u. Okay? If this term that comes out of this constraint for any VH and QH divided by the norm of VH, if I take the supremum over this, there must be a constant c so that this thing is greater or equal c times the norm of Q. Okay, so like I say, this is the inf-sup condition for this particular problem, for the Stokes equation. And here I have that the norm, the V norm here, this is the H1 norm, and the Q norm, this is the L2 norm for the Stokes equation. What you will see is that there's only sup here, there's no inf-sup. But what I can do is, of course, if this has to hold true for all Q, then certainly I can divide by Q, and then I can take the infimum over here, right? So Q doesn't appear on the right-hand side. So if there is such a C for all Q, then I can take the infimum on the left side. So I can reformulate the first equation in this particular way. I find the first equation sort of easier to understand. That's why I wrote it down. But in essence, what this says is I need to have finite element spaces VH and QH in such a way that such a C greater than 0 exists. I should have said that. So the constant C, of course, must be greater than 0. It must be independent of H such that this condition here is satisfied. So if you look at this in this particular form here, it becomes clear that if my space QH is too large, so if I have too many pressures, then the infimum will be smaller, okay, and maybe it becomes 0. So how do I, so let me assume that I have two spaces QH and VH that do not satisfy this equation here. How do I get to a situation where I do satisfy the condition? Well, I can do the following. So if it is not satisfied, then maybe I can make the space QH smaller. That would make the infimum larger. Or I make this VH larger, which would make the supremum larger. Okay, so I have two choices under which I can make sure that the condition is true. Either I make the velocity space larger, or I make the pressure space smaller. So it turns out that if I choose the typical finite element discretization for the Stokes equation, and I choose, for example, Q1 elements for the velocity and Q1 elements for the pressure, that the inf-sup condition is not satisfied. It just is what it is. It's not satisfied. A typical choice that does satisfy the inf-sup condition would be something that we call the Taylor-Hood element. So the Taylor-Hood element would choose the velocities out of the space pk plus 1 on triangles or qk plus 1 on quadrilaterals, and the pressure equals to pk and qk. Okay, so that means, for example, I would use bilinear elements for the pressure and biquadratic elements for the velocity. So I always choose the velocity one order higher than the pressure. That is what we call the Taylor-Hood element. And the Taylor-Hood element, I can prove, satisfies this equation. Okay, so when the equation is satisfied, essentially that means I have enough velocity so that the number of constraints is not a problem. Okay. Why do we do this? So you could think, so the Taylor-Hood element is pk plus 1 pk or qk plus 1 qk, the first one being the velocity and the second the pressure space. You could think, well, maybe I could have chosen pk pk or qk qk. And that is something that we can easily try out in step 22, for example. So if I do this in step 22, I get a pressure field that looks like this. Okay, so there's a singularity here which comes from the physical setup. So in step 22, what I do is I have fluid that flows in at the bottom, and then I have boundary conditions that pull it to the right over here and to the left over here. So I get a pressure singularity, and that's okay. But I get an oscillating pressure everywhere here. And that is a typical situation that you get when you have an element that does not satisfy the in-soup condition. We call this a checkerboard pattern. And it happens because the matrix has a near null space. That means that the matrix has a one-dimensional subspace in which it does not determine the solution. And this one-dimensional subspace happens to be exactly the one where the pressure is oscillatory. Now, why does the matrix have this near null space? That is because the in-soup condition is not satisfied. There exists such a C, but it is not independent of H. In particular, it goes to 0 as H goes to 0. Okay? So what this shows is that I cannot just choose pk pk or qk qk because I get these oscillatory modes and the solution does not converge. What I need to do, like I argued before, is I need to either make the velocity space larger or I need to make the pressure space smaller. Now, that of course leads to exactly the Taylor-Hood element. Right? The Taylor-Hood element does make the velocity space larger. Instead of qk, I choose qk plus 1. So for example, q2, q1, that's quadratic elements for the velocity and linears for the pressure, or cubic elements for the velocity and quadratic for the pressure. In that case, I can prove that there is a constant c greater than 0 that is independent of h. The matrix remains regular, the pressure is stable. So I get a picture that looks like this for the pressure here, that has a singularity that I expect from physical reasons, but the oscillations that were here everywhere, they're gone. Okay, so this works. Now, of course, I could also choose qk plus 2 and qk. So let's say cubic velocities and linear pressures, and the situation looks like before. So I have made the pressure even larger, so the in-soup condition is definitely satisfied. But that's wasteful, because now I'm in a situation where it is definitely stable, but I'm spending a lot of computational effort on the velocity field, but I have only piecewise constant pressures. And so what you will find is that the accuracy in your solution is limited by the piecewise bilinear pressures. And even though you have cubic velocities, you don't get the full accuracy that you expect from cubic elements because the pressure is such low order. So you can do this, you can choose qk plus 2 qk for the Stokes element, but it's not worth it. It's not computationally efficient. So to sum this up, I have found that qk doesn't work. qk plus 1 qk works. Now I might think maybe I can find something in between here, right? So I have somewhere between these two elements must be the line where the stability is or isn't satisfied. And I have two options. So either starting from this qk plus 1 qk from the Taylor-Hood choice, I could try to make the velocity space a little bit smaller, or I can try to make the pressure space a little bit larger. So option 1 is to make the velocity space a little bit smaller. That turns out to not work. So if I have, for example, q2 elements, then to make it smaller would mean that I have to take away shape functions. And that's not so easy. So the only shape function that I can take away is the one at the center. because all of the other ones, when I take them away, would mean that I end up with a discontinuous element, and a discontinuous element would be non-conforming for the Stokes equation. So it either doesn't yield unisolvency or it doesn't yield a continuous element. In either case, this is not a choice that leads anywhere. So I can't make the velocity space smaller. But I have option 2, namely I could make the pressure space a little bit larger than qk. So if you look at the bilinear form was grad v grad u h minus diff vh p h minus qh diff uh. So what you see is that on the pressure here and on the corresponding test functions, there's actually no derivatives. Okay? So we could argue, well, if there are no derivatives on these pressure functions, there is absolutely no need for them to be continuous, right? I don't need, for example, to have a weak derivative. There's nothing that forces me to do this. So I could, for example, choose pressure functions that come from the following space, namely the usual qk, so let's say bilinears in 2D, if I choose k equals 1, but then I'm also going to allow myself piecewise constant test functions. So I'm going to end up with a pressure space that contains all of the bilinears plus one function on every cell that is piecewise constant. Let's say that is 1 on that cell and 0 everywhere else. Okay, so I've made my pressure space larger. I've added as many shape functions to the pressure space as I have cells in my domain. And you can ask the question, well, does this satisfy the in-soup condition? And the answer is yes, it does. That works, right? So I can make the pressure a little bit larger, and what I would hope is that, of course, if I make the pressure a little bit larger, that I get more accuracy out of this, because I have more degrees of freedom. Whether that is true, that is sort of difficult to answer, because I don't quite know how to measure the error, right? I could measure the error in the L2 norm of the velocity, or the H1 norm of the velocity, or the L2 norm of the pressure. Or maybe I take the L2 norm of the divergence of u, which should be 0 but isn't, for UH. Depending on which norm I look at, I get errors that are either smaller or slightly larger. So as far as the error is concerned, the choice of the element, whether I take these constants to it or not, is not quite obvious. But I can. It's a stable element. I can go even further than this. So instead of just taking the bilinears and adding one piecewise constant function per cell to it, I might as well use a completely discontinuous element here. Okay? So let's say on every cell I would use bilinears for the pressure, but discontinuous. So instead of on average 1 shape function for the pressure per cell, I now have 4 shape functions per cell for bilinears. This turns out to not work. Now I have too many pressures. Okay, so if I enlarge my pressure space so much, then I end up with something that does not satisfy the in-soup condition anymore. Right? So the infimum over all QH has now become something that goes to 0 as h goes to 0. So practical choices. So I've said that I can either use the classical Taylor-Hood, qk plus 1 qk, or I could use the one where I enlarge the pressure by 1 piecewise constant per cell. In practice, we almost always choose k equals 1. That means quadratic elements for the velocity and linears for the pressure. And why is that so? So you could argue the same way as we did for the Laplace equation. I might as well choose k equals 2 or k equals 3, because that gives more accuracy. But it turns out for the Stokes equation, because it has so many components, right? There's all of the velocities plus the pressure, that it turns out you get a lot of degrees of freedom if you go higher order. So we can do this here. So if you look at, this is a sketch of this finite element space. So every blue line would correspond, let's say, to an x velocity, and that's a Q2 element. Okay, so it has 9 degrees of freedom for the x velocity. It also has 9 degrees of freedom for the y velocity. These would be the red lines. And then it has 4 pressures. That would be the Q2, Q1, the traditional Taylor-Hood approach. So if you add this up, 9 for the x velocity, 9 for the y velocity, and 4 for the pressure, you end up with 22 degrees of freedom per cell in 2D. And in 3D, you end up with 89. Okay, so that's already a lot of degrees of freedom per cell. Now, if you ask the question on a uniform mesh, how many elements do you get per row of the matrix? So consider, for example, this 1 degree of freedom. Let's say this pressure degree of freedom here for the Taylor-Hood element. How many degrees of freedom how many other degrees of freedom does it couple with? Well, it couples, the shape function for this pressure lives on these 4 cells, and it couples with every single shape function that are on these 4 cells, of which in 2D there are 59. And if you do the same sort of computation in 3D, you would realize that this one pressure couples with 402 total degrees of freedom. So in every row of this matrix, you have 402 non-zero entries. That's still a sparse matrix. So if you think of a sparse matrix as just being, let's say, the 5-point stencil or a 7-point stencil in 3D, then that's a very, very sparse matrix. I think in reality, for real problems, we're quite comfortable with, let's say, a few hundred degrees of freedom per row. So when you solve a Stokes problem in 3D with Taylor-Hood, you have 402 non-zero elements per row. Of course, in a matrix that might have a few million by a few million, 402 is not that many. But of course, it is still a concern as far as, let's say, memory consumption is concerned. There's a lot of entries that you need to store in every row, and that means for every degree of freedom in your DOF entry, you have to store 402 non-zero entries per row. So that's only for the Taylor-Hood Q2, Q1 element. If you go to, let's say, even higher Q3, Q2 elements, you would immediately end up with a few thousand. So I think I calculated this yesterday, and Q3, Q2 would be well over 1,000 degrees of freedom, well over 1,000 non-zero entries per row already. So that's sort of the practical reason why we almost never go beyond Q2, Q1, because it just poses practical problems. All right, so I've told you about Stokes. Now let me show you the other prototypical example of a saddle point problem, or of a mixed problem, named the mixed Laplace. So in a mixed Laplace, we have u equals minus grad p, or u plus grad p equals 0, and diff u equals f. And that again, I can rewrite this as a minimization problem, namely I want to minimize the norm of u, okay, subject to diff u equals f. And in variational form, that means diff u times q equals q times f for all q in our test space. So if I make this into a discrete variation formulation, then it gives me something like this, and the discrete minimization problem looks something like this. So again, I have as many constraints here as I have elements in my space QH. Okay. So I can look at what the corresponding inf sup condition would be in this case, and the inf sup condition looks very similar to before, okay, except that my spaces are slightly different. So V is now HDiff and not H1. But so this is the condition, and I will be in exactly the same situation, that I need to choose the velocity space large enough to satisfy this, or I need to choose the pressure space small enough. Okay, so I cannot choose the velocity and the pressure spaces independently for this, for the mixed Laplace. I have a coupling condition that requires me to choose them in concert. So common choices would be, I can go with the Taylor-Hood example again, right? So I can choose the velocity as qk plus 1, and the pressure is qk, or on triangles and tetrahedra, I could use pk plus 1 and pk. And we can play exactly the same game, namely, can I make the velocity space smaller, because that would yield less numerical effort for essentially the same accuracy, or can I make the pressure space larger, namely, because I wanted to get better accuracy with only slightly more work. And so this is, in all saddle point problems, you always live in that tension. You want to make the pressure space as large as possible, or the velocity space as small as possible. And we argued that in the Stokes case, I couldn't make the velocity space smaller, but I can make the pressure space larger. Now for the mixed Laplace, I show you the opposite case, where I can make this the velocity space smaller. And to see how that works, let me look at the bilinear form again. So at the bilinear form, so this was for Stokes, okay? This is for mixed Laplace, and the difference lies in this first term. This comes out of the Laplace u in the Stokes case, and here I just have u in the in the mixed Laplace. So you see that in this case here, in the Stokes case, I actually needed gradients of u. So let's say weak gradients. I can only achieve this when I have elements that are continuous. Okay. Here, I don't need this, but I do need that I have divergences of my velocity fields. Okay, so I don't need full gradients. All I need is that the divergence is defined in some weak sense. And that allows me to make my velocity space smaller. Namely, I want to choose a velocity space that does not have quite as many degrees of freedom as qk plus 1. I want to make it smaller, and I want to do this in such a way that maybe these functions are not continuous anymore, but that only the normal derivative is continuous. Not the normal derivative, the normal component of these vector fields is continuous. That's all I need. In order for the divergence to be defined in a weak sense, all I need is that at cell edges, the normal component of the velocity field is continuous. And that's exactly the Raviat-Thomas element. So the Raviat-Thomas element satisfies this sort of condition that the normal component is continuous. And I can use this Raviat-Thomas K element with qk as a pressure space, or I can use the lowest order Raviat-Thomas element with piecewise constant pressures. So that's one option. I can also make the pressure space larger. Okay, so I could use the qk element, so Raviat-Thomas and qk, or like I said before, or I can choose the same Raviat-Thomas element, and I can make the pressure space larger than I had here. So I can go from qk to dgqk, so the discontinuous qk elements. Okay, and in that case, it still remains stable. So I have made this space of velocity smaller and the space of pressure slightly larger, but still in a way so that they satisfy the inf-sup condition. There are quite a number of alternatives to this. So the Raviat-Thomas element is not the only element that allows me to form divergences. There are also the Bretzi-Douglas-Marini, the Arnold-Falk-Winter, and many other elements that satisfy this sort of condition. So in this, when you have HDiff problems, there is a vast number of elements that all are made exactly for this sort of situation. But in general, most of them use piecewise constant pressures at the lowest order. Let's say the ones that have been used in the past, they lead to very slow convergence, and if you wanted to use them in applications today, you would want to use higher order elements. In contrast to Stokes, these elements are relatively sparse. The velocities do not have a lot of degrees of freedom, and as a consequence, the matrix does not become full until maybe you have something like let's say k equals 3, for example. So for the mixed Laplace, if you make the velocity space smaller than qk plus 1, then you can typically go to higher order. So with this, I would like to end this section on how to choose finite element spaces for mixed problems. I hope you have seen that we have this constraint, this inf-sup condition that we have to satisfy, and that we cannot just use the velocity in the pressure spaces independently, or in general for saddle point problems, we cannot choose the two components independently, but they have to satisfy this compatibility condition. And that we can be on the safe side, for example, with the Taylor-Hood element, or that we can try to push the gap a little bit smaller by choosing one or the other, smaller or larger. But we always have to respect that inf-sup condition. If we don't, we end up with solutions like the one that I showed you for the pressure case, where you end up with spurious modes, like the oscillations.